Okay, so this is problem 1. In this one, we've got a disc with a mass of 3 kilograms and a radius of 0.50 meters, and it accelerates from rest at a constant rate of 1.0 radians per second. And in the first part, we're asked to write an expression for the angular speed with respect to time. So to do this, we'll need to use our equation. Omega is equal to omega naught plus alpha t. Now, we're told that it starts from rest, so that tells us that omega naught is 0, and we've got alpha is 1.0. So this is equal to 1.0 t, or we can just write it as t. In part B, it then asks us to write an expression for the angular displacement with respect to time. So for this equation, we'll have theta is equal to theta naught plus omega naught t plus a half alpha t squared. Now in this case, we're told to assume that it starts at theta equals 0. So this term here is 0. Initially it's at 0. We know that it starts from rest, so this term here is 0. So we've just got a half alpha t squared. So in this case, this is equal to a half times 1 times t squared, which is just equal to 2 squared on 2. Now in part C, it says what torque acts perpendicular to the radius of this disk to cause this acceleration. So to do this, we're going to need to use that the net torque is equal to I alpha. We've been given alpha and we can calculate I. Because it's a disk, we know that I is given by a half mr squared. So this is equal to a half times 3 times 0.50 squared. And so solving this one on the calculator, we get 0.375 meters squared kilograms. So now what we can do is substitute this into here. So we've got 0.375 times 1.0, and that is equal to 0.375 Newton meters, but we should give our answer to 2 significant figures, as everything else is given to 2 significant figures. So this is 0.38 Newton meters. Okay, this is question 2. In this one, we've got a particle with a mass of 0.10 kilograms, and it's traveling around a circular path with a radius of 2 meters. So let's just sketch that here. We've got radius is equal to 2 meters. And we're told that the angular acceleration is given by 1.0 t plus 0.10 radians per second. And in the first part, we're asked to write down an expression for the tangential acceleration of the particle. Okay, so the tangential acceleration is related to the angular acceleration through at is equal to alpha r. So we can just substitute in, we've got 1.0 t plus 0.10 times 2, and so this is equal to 2.0 t plus 0.20 meters per second. Now in part B, we're asked to get an expression for the radial acceleration. So the radial acceleration is equal to v squared over r, or omega squared r. So this is the easier one to calculate in this case. Now we've got alpha, and alpha is equal to d omega dt. So we can say, well, d omega is equal to alpha dt, and we can integrate. Now we're told that this starts from rest, so we've got 0 as the initial omega up to omega at time t, and that's at time 0. So we've got omega is equal to the integral, let's substitute in, we've got 1.0 t plus 0.10, and this is dt from 0 to t. So doing this integral, we've got 1.0 t squared on 2 plus 0.10 t, and we're evaluating from 0 to t. When we put in 0 to both these terms, it's just 0. So when we evaluate this, we end up with a half t squared plus 0.10 t. Okay, so now we've got omega, so now we can go back and get our radial acceleration. So our radial acceleration is omega squared, so 0.50 t squared, that's this, plus 0.10 t, and that's squared, times the radius, which is 2. So let's do the maths. We'll expand the brackets. So we've got a half times a half, which is a quarter, 0.25 t to the 4, plus there'll be 2 times 0.50 times 0.10. So that is equal to 0.10 t cubed plus this term squared, which is 0.010 t squared, and then that's times 2. So multiplying everything inside here by 2, we get 0.50 t to the 4 plus 0.20 t cubed plus 0.020 t squared as our radial acceleration. Then in part C, we're asked to evaluate the magnitude of the acceleration at t is equal to 1 second. So the magnitude of the acceleration is equal to the square root of the tangential acceleration squared plus the radial acceleration squared. So what we need to do is evaluate each of these at t is equal to 1 second. So if we do that, let's evaluate this in blue at t equals 1 second. Then we've got 2 plus 0.2, and this is equal to 2.2. And then we evaluate this one also at 1 second. So this is 0.50 plus 0.20 plus 0.02. So that's equal to 0.72. So then what we can do is substitute both of these into here. So when we do that, we get the square root of 2.2 squared plus 0.72 squared. And solving that on the calculator, we get 2.3 meters per second per second. Okay, so in this one, we've got these 5 spheres, all with mass m, and they're pivoted about an axis here. These first ones, the closer ones, are a distance r from the pivot point, and the further ones are both a distance 2r from the pivot point. And then the first part, we're asked to calculate the moment of inertia, which is just equal to the sum of mr squared. So we just need to sum this for each of these masses. So this first mass, this is m times it's a distance 2r squared. The second mass, that's a distance mr squared. Plus this next mass, this is 0 distance from the pivot point because it's on the pivot point. So this is m times 0 squared. Plus this one, which is m times r squared, plus this one, which is m times 2r squared. So this is equal to 4mr squared plus mr squared plus that's 0, mr squared plus 4mr squared. So we've got 4 plus 1 plus 1 plus 4, which gives us 10mr squared as our moment of inertia for this figure. Now in part B, it says that it experiences a torque tau, and it asks us for an expression for omega. So there's a couple of steps we'll need to take. First of all, we'll need to use Newton's second law, which tells us that the torque is related to the angular acceleration through torque is equal to I alpha. So we can calculate the angular acceleration, which is torque over I, which is equal to the torque over 10 mr squared. And then we'll need to relate the angular speed to the angular acceleration. We're told that it starts from rest, so we know that omega is equal to omega naught plus alpha t. This is 0, so omega is equal to alpha t. So this tells us that since we've got alpha here, we've got omega is equal to tau times t over 10 mr squared is an expression for the angular speed of this object experiencing the torque tau. Okay, this is problem 4. On this one, we're given a rod with a uniform mass density. It's got a total length L and it's pivoted about a point here, where this is L on 3 and this length here is 2L on 3. It's got some mass M. So we can write the linear mass density, which is the mass over the length, this way. And what we're going to want to do is split it up into lots of little bits. So we'll consider a little bit here, which is a length x from this axis and has length dx. And where we're considering this little bit, dx, it's got a mass dm equal to the linear mass density times its length, which is equal to m over l dx. Okay, so in order to do this, we'll need to use our equation that the moment of inertia is the integral of r squared dm. So what we'll want to do is sum everything on this side and sum everything on this side. And by sum, I mean integrate, because integrate is literally summing, but it's what we use for continuous objects. So we will want to go from from 0 to L on 3. And then we're calling the distance of our little increments from the pivot point x. So this is x squared times dm. Plus we'll want to sum the bits on this side. So on this side we're going from 0 to 2L on 3 of x squared dm. Now what we'll want to do is we'll want to make this substitution for dm here. dm is equal to m on l dx. So we can write this as the integral from 0 to L on 3 of x squared times m on L dx, plus the same thing here, 0 to 2L on 3 now, x squared times m on L dx. Okay, now we'll move the m on L out the front of the integral because it's just a constant, and then we're integrating from 0 to L on 3 of x squared dx. And we're doing the same thing here, but we've got different limits. So it's m on L from 0 to 2L on 3 of x squared dx. Okay, let's do this integration. So when we integrate x squared dx, we end up with x cubed on 3. And our limits are going from 0 to L on 3. And then we've got plus m on L times x cubed on 3, now from 0 to 2L on 3. Okay, now we substitute our limits in. So we've got m on L. Now this is equal to L on 3 all cubed. So that'll be L cubed over 27. And then we've still got this times 3. And when we put in the 0 for x, it's just 0. So we're not subtracting off anything. And then we've got m on L. And in this case, we're cubing this. So 2L cubed, that's 8L cubed. Over on 3, that's on 3 squared, which is 27 times 3. Okay, so we have 27 times 3 is 81. So we've got, let's cancel out this L and make this instead of an L cubed, it's an L squared. And we'll do the same thing here. So we've got ML squared over 81. And this one here is plus 8 ml squared over 81. So this is equal to 1 ml squared on 81 plus 8 ml squared on 81. So that's 1 plus 8, which is 9 ml squared on 81. But then 81 is just 9 times 9, so we've got a common factor there. So we can write this as ml squared on 9. So that is how we calculate the moment of inertia when it's pivoted about this point a third of the way along the rod. Okay, this is problem 5. We've got a pedal arm here. So it's pivoted about some point here, and then the pedal's at the end here, and this distance here we're told in the question is 0.152 meters, and then a force is applied down here, which is equal to 111 newtons, and we're given different angles between the radius. So the direction of the radius is this way from the pivot point to where the force is applied, and this in here is our angle phi. So the way I've drawn it at the moment, phi is 90 degrees, but in the question we get given different values for phi. Okay, so in part A, we're told that the angle is equal to 30 degrees, and we're asked to calculate the torque. So we know that the torque is given by R cross F, which we can write as RF sine phi. So we can substitute in, we've got 0.152 times 111, and in the first part, phi is 30, so this is times sine 30. So solving that one, we end up with 8.4 Newton meters. Now in the next part, we're told that phi is equal to 90 degrees. So like I've drawn it up here. And in this case, the torque is equal to RF sine 90. So that's 0.152 times 111 times sine 90. Sine of 90 is just 1. So solving that, I get 17 Newton meters, where I've given it to two significant figures. Just because everything's given to two significant figures. This was to two significant figures too. Then in part C, we're now told that phi is equal to 180 degrees. So this is, for example, when the pedal's up like this, then the radial vector's like that, and my force is down like that. So there's 180 degrees between those two. And in that case, the torque is given by 0.152 times 111 times sine of 180. But sine of 180 is 0. So this whole thing is equal to 0 Newton meters. Okay, so this is problem 6. In this one, we've got an Atwood-like machine. So it's got some radius r, and we're told that r is equal to 5 centimeters. And then it's got two hanging masses. We've got M1 here, where M1 is equal to 460 grams, and M2 over here, where M2 is equal to 500 grams. And then these have different tensions in the string. So in this string, we've got tension T1. In this string here, we've got tension T2. We're told that it's released from rest and that block 2 falls 75 centimeters in 5 seconds. Now, in the first part, we're asked what is the magnitude of the acceleration of the blocks. Okay, so we know how far it falls and how long it takes. So we're actually going to need to use our kinematic equations to calculate the size of the acceleration. So we can use our equation S is equal to ut plus a half at squared, where we know it falls from rest. So this one is 0. And so rearranging this, we've got a is equal to 2s, where s is the displacement it falls through, over t squared. So now we can substitute in, because we got given these values in the question. So this is 2 times 75 centimeters, which is 0.750 meters, divided by t squared, which is 5 squared. So solving that on the calculator, we end up with 0.0600 meters per second as the acceleration. So it's accelerating relatively slowly, which is what you expect because these masses are fairly similar to each other. Part B then asks us what is the tension in this first string T1 here. Okay, so to do that, let's consider the forces acting on M1. So we've got M1G pulling it down, the weight force, and then we've got this T1 force pulling it up. Now, because the second mass is heavier, we can see that this is going to move in a direction like this. So M1 will be accelerating up while M2 is accelerating down, which we also know because we were told that M2 falls in the question. Okay, so using Newton's second law, we can write, well, M1A is equal to T1, which is pulling it up, minus M1G, which is pulling it down. So T1 is equal to M1A plus M1G, and these are all values that we have. So let's write this as M1A plus G, just to save ourselves some space. So M1 is equal to 0.460 kilograms times A, which we've calculated here, so 0.0600, plus G, which is, we can use 9.80. Solving that on the calculator, we end up with 4.54 newtons. Part C, we're then asked to find what's T2 equal to. So we do a similar process for the other block over here. So we've got M2G pulling it down. In this case, this is a slightly larger force, and T2 pulling it up. So we can write, well, M2A is equal to M2G minus T2. And so rearranging this, we've got T2 is equal to M2A plus G, and we can substitute in here. So we've got 0.500 times 9.80, so that's the G, then plus the A, which is the 0.0600. And solving that one on the calculator, we end up with 4.87 newtons. So these two tensions are slightly different. Now with part D, because this isn't slipping, the acceleration, the tangential acceleration on the edge of the ring must be the same as the acceleration of the two blocks. So we can use our equation that alpha is equal to A over R, and we've calculated A up here, 0.0600, and R, that's the radius, which is 5 centimeters, so that's 0.0500 meters. And so doing this, we get 1.20 radians per second as our angular acceleration. Now in part E, it has asked us to calculate the rotational inertia. So in order to do this, we're going to need to use Newton's second law for rotation, which tells us that I alpha is equal to the net torque. Now, we've got two torques acting on this disc. We've got the tension in this string, which is pulling it back this way, and the tension in this string, which is pulling it round this way. So we've got T2 acting here and T1 acting here, and torque is equal to R cross T in this case. And so we can write this as RT2 minus RT1. So in this case, with the cross product, the radius and the tension forces were acting at 90 degrees to each other. So there's a sine 90 in there, which is just 1. So this is equal to R times T2 minus T1. Okay, so what we're trying to calculate is I, so we can rearrange this and write, well, I is equal to R T2 minus T1 over alpha. So now we can substitute in. We've got 0.0500 times T2, which we calculated here. It was 4.87 minus T1, which we calculated here, 4.54. Divided by alpha, which we calculated here and was 1.20. So solving that, we get 0.0138 kilograms meters squared. Okay, so this is problem 7. In this one, we've got a cylinder here. Now, it's got a little radius here, which we'll need. Is given by R, and R is equal to 5 centimeters, and then it's got a bigger radius here, which is capital R, and that R is equal to 12 centimeters. And we've got a number of forces acting on this. So at this point here, we've got force 1, which is equal to 6.0 newtons. So as we're drawing each of these forces, let's just look at the relationship between the radial vector and the force, because we are going to have to calculate torques. So for this one, we've got R going in this direction, and we've got the force going in this direction at 90 degrees to it. And this one is making the cylinder try to spin in a counterclockwise direction that way. Now over here, also at radius R, we've got another tangential force here acting F2, which is equal to 4 newtons. And if we look at our r vector here, it's going this way, and then F is going that way. So this one's trying to make this cylinder spin in a clockwise direction this way, and the angle between the radial vector and the force is once again 90 degrees. Now we've got a third force acting down here, F3. This is acting at a distance from the center of the cylinder of little r, so 5 centimeters, not on the edge of the cylinder. So for this one, we've got our radial vector r this way and then F going down. So once again, there's 90 degrees, and this one is trying to make it rotate this way. And then finally, we've got a fourth force acting over here. This one's acting in this direction, F4, and it is equal to 5 newtons. Now in this case, because our radial vector is going this way and our force vector is going in the same direction, so they're parallel, so their cross product 0, so there is no torque from this one. Okay, so now we've drawn everything onto our little diagram. Let's look at the question. It asks us to find the magnitude and direction of the angular acceleration of the cylinder. So in order to do that, we're going to need to make use of Newton's second law for torques, which tells us that I alpha is equal to the sum of the torques. And in this case, you can see that we've got 4 forces acting on it, so we'll have 4 torques, except that this one's 0, so really just 3 torques. And because it's a cylinder, we know that I is equal to a half mr squared, and in this case it's capital R because it's the radius of that cylinder, and we're told in the question that the mass of the cylinder is equal to 2 kilograms. So we can calculate this here. This is equal to a half times 2 times 0.12 squared, and solving that on the calculator, we end up with 0.0144. Okay, so alpha is equal to the sum of the torques over I. Let's do the sum of the torques. So this is going to be force 1 times the radius, because that's the point at which this one's acting. Now let's take the counterclockwise torques as negative and the clockwise ones as positive. So we'll put that one as negative. Now this second torque is going to be equal to F2R, and then we've got this third torque, which is F3R, and then we ignore this one because it's 0, divided by I. So now we can substitute in. We've got minus 6 times 0.12 plus 4 times 0.12 plus F3, we're told in the question, is equal to 2. So let's put that in, 2 times, now this is acting at the smaller radius, so times 0.0500, divided by I, which we've calculated up here, which is 0.0144. So solving that one on the calculator, we end up with minus 9.7 radians per second, which is, we can write as 9.7 radians per second counterclockwise. Okay, so this is problem 8. In question 8, we've got a rod which is pivoted about one end and it's allowed to swing like a pendulum. So something like that. It's pivoted about this point. It's got a length here of 0. It's got a length of 0.75 meters and a mass of 0.42 kilograms, and then it swings like a pendulum. So it's going to end up at some time like this, and then at this lowest point, we're told in the question that the angular speed is equal to 4 radians per second. Then it swings up to this higher height on this side, like that. Okay, so in the question, we're asked to find the rod's kinetic energy at its lowest point. So we want to find the kinetic energy down here. So to do that, we're going to need to use our kinetic energy for rotation formula, which is a half I omega squared. Okay, so possibly you remember the moment of inertia of a rod. If not, we can calculate it using I is equal to the integral of r squared dm. If you've just recently done question 4, you probably remember how to do this one by breaking it up into little increments, each with length dx, each a length x from the end there. And so dm is equal to the mass over the length, the linear mass density times dx. And so this is equal to, we're doing the integral along the rod, so from 0 to L of x squared times m on L dx. So pulling the m on L out the front, we're going from 0 to L and we've got x squared dx. So we want to solve this integral, which is m on L. When we integrate it, we get x cubed on 3. And this is from 0 to L. When we put in 0, it's just 0, and so this is equal to ml times L cubed on 3. So this is equal to ml squared on 3. So that's the moment of inertia of our rod. So we've got I here. We told omega in the question, and so we can just substitute in now. So this is equal to a half times m, which is 0.42, times L squared, which is 0.75 squared, over 3 times omega squared, which is 4 squared. So solving this on the calculator, we end up with 0.63 joules. So that's the answer to part A. Now in part B, it asks us how far above that position the center of mass rises. Okay, so our center of mass at this position is here. And at this point, all the energy is in the form of kinetic energy, and then it rises and the center of mass is here in the middle of the rod, and we need to work out what's this change in height here. Now at this highest point, we don't have kinetic energy, all the energy is in the form of potential energy. So we need to make the assumption that energy is conserved. So we've got mg delta h, which is that delta h there, is going to be equal to the kinetic energy here, so 0.63 joules. So delta H will be equal to 0.63 over m, which is 0.42, times 9.8, and solving that we get 0.15 meters. Okay, so this is problem 9. So this is a bit of an involved projectile motion one. So on this one, we've got a cylinder rolling off a roof. Now, the length it rolls along is 6 meters, and this angle in here is theta. So it comes to the bottom of the roof, and then it undergoes projectile motion down to the ground, which is 5 meters away. So the first thing we need to do is calculate its speed when it gets to the bottom of the roof. To do that, we're going to need to know the height that it rolls from. So using some trigonometry, we can see that this height here is equal to the length, which is the 6 meters, times sine of this angle here, which we're told in the question is 30 degrees. So sine of 30 is a half, so this is equal to 3 meters. Now in the first part of the question, we're asked for the angular speed, so we need to find omega. In order to do that, it's easiest to use our energy considerations. So the initial potential energy, which is given by mgh, goes into kinetic energy, and we've got the translational kinetic energy, a half mv squared, plus the rotational kinetic energy, a half I omega squared. And because this is a cylinder, I is equal to a half m r squared, and we know that omega is equal to v on r. So we can substitute these in, and we've got a half mv squared, this first term, plus a half times I, which is a half mr squared, plus omega squared, which is v squared on r squared. And these r squareds then cancel out. So we've got a half mv squared plus a half times a half, which is a quarter, times mv squared. So this is equal to 2 quarters mv squared plus 1 quarter mv squared. So this is 3 quarters mv squared. So we can use this to get the velocity of the cylinder as it's launched from the roof. So we've got mgh is equal to 3 quarters mv squared. These cancel out, and we've got v squared is equal to 4/3 gh, which tells us that v is equal to the square root of 4/3 gh. Now, it will be useful later to actually have this value, so let's calculate it now. This is 4/3 times 9.80 times h, the height from which it rolled, which we've calculated up there was 3 meters. And so solving this on the calculator, we end up with 6.26 meters per second. Okay, but that's not what we were asked for in this question. In this question, we were asked for omega, which is given by v on r. So we're getting close. So omega is equal to v, which is the 6.26, over r, which is the radius of the cylinder. Now, in the question, we're given that value. We're told that the radius of the cylinder is equal to 10 centimeters. So that's divided by 0.10 meters. And so this is equal to 62.6 radians per second, which we can write as 63 radians per second to 2 significant figures. Now, in part B of the question, it asks us how far horizontally from the roof's edge does the cylinder hit the level ground. Okay, so now we're trying to work out this range here. So to do that, we'll need to consider the horizontal and vertical components separately and start by calculating time to ground. Now, the thing to remember here is that it isn't initially traveling in the horizontal direction. Initially, it's traveling with our speed v, which we calculated here, 6.26 meters per second, and that's in the direction of the roof. So this is 30 degrees, and we've got a horizontal component to that. Sorry, this is pointing in the wrong direction. The horizontal component is pointing this way, and the vertical component. So the vertical component is given by 6.26 times sine 30, which is equal to 3.13 meters per second, and the horizontal component is given by 6.26 times cos 30, which is equal to 5.42 meters per second. Okay, so to calculate the time to the ground, we'll need to use the vertical component. We know how far it falls through. We've got its initial speed, which isn't 0, and we know that it's accelerating downwards at 9.8 meters per second. So we can use Sy is equal to Uyt plus a half Ayt squared in order to calculate the time. So Sy, that's 5 meters, is equal to Uy, which is minus 3.13. Then the minuses here all represent that it's going downwards, plus 9.8, that's downwards, so this will be a half times 9.8 times t squared. So we can rearrange this and write, well, 4.9 t squared plus 3.13 t minus 5 equals 0. So we can now solve this to get time. So to do that, we'll need to use our quadratic equation. So t is equal to minus b plus or minus the square root of b squared minus 4ac on 2a. So b, that's the thing in front of the t. So we've got minus 3.13 plus or minus the square root, 3.13 squared minus 4 times a, which is the thing in front of the t squared. So that's 4.9 times c, which is minus 5. So I'm going to make this into a positive here. And then we divide by 2a, which is 2 times 4.9. Now, we want a positive time. We want it to fall on the ground after it left the roof, not before it. So we'll take the positive square root here. We'll ignore this negative one. And so when we do that, we end up with minus 3.13 plus 10.38 over 9.8, which is equal to 0.740 seconds. So now we have the amount of time it spent in the air. Now, if you're not happy with the quadratic equation, another way to do this is to use v squared equals u squared plus 2as, and you can use this to calculate the speed when it hits the ground, and then you can use v equals u plus at to calculate the time. Okay, but now we have the time and we're trying to get the distance it travels. So to do that, we'll need to use horizontal component, and we will use s equals ut plus a half at squared, but there is no acceleration in the horizontal component, this term's 0, so we've got sx is equal to uxt, and ux, that's the initial velocity in the x direction, which is 5.42, and t, that's the time in the air, which we've just calculated here. And so solving this on the calculator, we end up with 4.0 meters, and that's to 2 sig fig. So the projectile motion part there was fairly involved. Okay, this is problem 10. So in this problem, we've got a massless rod here. And we've got two skaters, both with a mass 50 kilograms. Now they both rotate around the center of the rod here, and we're told that the rod initially has a length of 3 meters, and when the skaters come in, they're moving in opposite directions, each with a velocity of 1.4 meters per second. Now in the first part, we're asked to consider the two skater system, and we're asked for the radius of the circle. Now this question isn't especially clearly worded, but it's essentially asking us what's the radius that the center of mass moves about, and the answer is that the center of mass doesn't move. The center of mass does not move. So radius of circle of center of mass is 0. The radius of the circle that the two individual skaters trace out is both half this length, so it's both 1.5 meters. It's the radius for the skaters. Individual. Okay, now in part B, it asks us the angular speed of the skaters. Okay, so to do this one, we'll need to use omega is equal to v over r. We know for each of the individual skaters that they're going at 1.4 meters per second, and we know that the radius is 1.5 meters. So we're just doing 1.4 divided by 1.5, and when we do that on the calculator, we get 0.93 radians per second. Now part C asks us for the kinetic energy of the two skater system. Okay, so we've got kinetic energy is given by a half I omega squared, and in this case we've got both the skaters, so we'll have to do this for both the skaters. I for each skater is just given by mr squared, because we're just treating them as point masses. So this is equal to 2 times a half times the I, which is the mr squared, so that's 50, times the radius squared, which is 1.5 squared, now times omega squared, so that's 0.93 squared. So solving that one on the calculator, we end up with 98 joules. Now, sorry, part D. Now in part D, we're told that the skaters pull themselves along the rod until they're separated by 1 meter. So here's the center of mass. Here's skater 1, here's skater 2. This is 1 meter, and the radius of each individual skater is 0.5 meters. And we're asked to calculate their angular speed. So to do that, we're going to assume angular momentum is conserved. So the sum of I omega initial is equal to the sum of I omega final. Okay, so we'll want to use this equation here for I, and the radius of this is changed. So these i's will be different between the two sides. So let's write it out. We've got the two skaters that we need to consider in each case. So we've got the mass times the initial radius squared times omega initial, plus for the second skater the mass times the initial radius squared times omega initial, and that will equal afterwards the mass times the final radius squared times omega final plus the mass times radius final squared, this is for the second skater, times omega final. Okay, so m occurs in every single term, so we can just cancel it out. So here we've got 2 radius initial squared omega initial is equal to 2 radius final squared omega final. So we're trying to get this omega final, so rearranging omega final is equal to radius initial squared over radius final squared times omega initial. And the initial radius was 1.5 squared, the final radius was 0.50 squared, times omega initial, which was 0.93, and that gives us 8.4 radians per second is the angular speed of the skaters afterwards. Now part E asks us for the kinetic energy of the system, so we're just going to do what we did up here in step C. So we'll have the kinetic energy is equal to 2 times a half I omega final squared. So this is equal to I, which is mr squared, so 50, times the radius squared is now 0.50 squared, times omega final squared, which is 8.4 squared. And solving that, we end up with, to two significant figures, 880 joules. Now, we can see that they've gained kinetic energy. So in part C, they had 98 joules, but now that they've moved themselves closer to the center, they've got a higher kinetic energy, 880 joules. So part F is asking what provided the energy for the increased kinetic energy. And the only thing that could have provided it is the work done by the skaters. So the skaters have done work in order to move themselves along the rod and increase the kinetic energy. So the skaters have done work to move themselves along the rod.